Welcome back, explorers, to another incredible journey on Saltwater Stories.
Hello, everyone.
Today we are putting on our warmest imaginary gear. Forget the sunny shallows for a bit.
Yep, we're going somewhere really different. Think dark, think cold, think deep, really deep.
We're heading to the bone-chilling waters of the Arctic and the North Atlantic, some of the most mysterious places on Earth.
It's a realm governed by, well, almost total silence and crushing pressure. The cold down there is so intense. I mean, if it were fresh water, it'd be solid ice.
Wow.
And we're going to meet a creature that just, it defies everything we think we know about life. A living legend, really. It's been swimming through centuries of human history.
Well, we barely even knew it existed.
Exactly.
Okay, to get us started, I want you to imagine something. Close your eyes, maybe.
Yeah.
Picture yourself near the North Pole.
Brr. Okay, I'm there.
You're in a tiny submarine, super strong, built to go deep, and you're sinking. Down.
Past where any sunlight can reach. It's just black outside.
Totally black. The only light is from your sub's floodlights, cutting through the dark water. What do you see out the window?
Well, as you sink, you'd see these tiny white flakes drifting down constantly. Scientists call it marine snow.
Marine snow, like snowflakes underwater.
Sort of. It's actually tiny bits of dead stuff, plankton, fish scales, other gunk sinking from the surface, food for the deep sea.
Okay, got it. And it's cold.
Yeah.
Really cold. You can feel the pressure, right? The sub might even groan a little.
Oh, yeah. It's a lonely, quiet, ancient feeling place down there. Very few things live this deep.
And then, suddenly, your floodlight catches something. It's not marine snow. It's big.
A shape, just sort of materializing out of the darkness.
Huge, massive. And it's moving so slowly. Impossibly slow, like it's not even swimming, just drifting.
Thick, powerful body. Longer than a pickup truck, easily. Almost looks like a giant gray log that somehow came alive.
Silent too, right? Like a ghost.
Utterly silent. As it floats closer into your light beam, you see this rounded snout and these two pale, cloudy-looking eyes. Small eyes for such a big creature.
Does it see you? Does it react?
Doesn't seem to. It just passes by, completely unhurried, maybe doesn't even notice you're there. And then, poof, it just melts back into the blackness.
Wow. What an encounter. That silent, shadowy giant, everyone, is the Greenland shark. Its official name is Somniosus microcephalus.
The ancient grandparent of the deep, a living time capsule, and honestly, still one of the biggest mysteries on the planet.
So that's our mission today. We want to really get to know this incredible animal. We're going to explore its amazing records, its super cool body design, and figure out how it survives where almost nothing else can.
Get ready, because this shark breaks a lot of rules.
Right. So the Greenland shark, it's not just any shark. It's what you might call a creature of superlatives.
Superlatives, you mean like best in show, holds records.
Exactly. It holds some major world records, not just for sharks, but for like the whole animal kingdom. It's a real standout.
Okay, lay some on us. What makes it such a record breaker? I bet size is one, right? It sounded huge in the story. Oh, definitely. It's one of the largest carnivorous sharks out there. Eating meat, that is. They regularly get up to, say, 21 feet long.
21 feet, that's longer than my living room.
It is. And some reports from older, really big ones suggest they might even get close to 24 feet. Think about that, the length of a small school bus.
And heavy, too, I bet.
You bet. We're talking over 2,200 pounds. That's more than a small car. Just this massive, hefty animal.
Wow. Okay, biggest. What else? Fastest.
See, that's where it gets weird. Despite being enormous, it holds the record for being the slowest swimming shark ever measured.
Lowest. A giant shark is the slowest. That seems wrong.
It's totally counterintuitive, isn't it? But it's true. Its cruising speed is incredibly slow. We'll get into why later, but yeah, slowest swimmer.
Okay, slowest. What about where it lives? You said deep and cold. Record-breakingly deep and cold.
Yep. It's the undisputed champion of cold, deep water. They're regularly found swimming around at depths of 3,900 feet. That's really deep.
3,900 feet. I can't even picture that.
And that's just regular. They've actually been spotted using remote cameras and stuff as deep as 7,218 feet.
Whoa. That's nearly a mile and a half straight down. The pressure must be insane.
Unbelievable pressure and pitch black, freezing cold. It's an environment most creatures just couldn't handle.
Okay, biggest, slowest, deepest, coldest. What's the ultimate record? The one that blows everyone away.
The big one. The absolute showstopper. The Greenland shark is officially the longest living animal with a backbone on the entire planet.
Wait, longest living
Huh?
animal, like older than giant tortoises, older than those super old clams.
Older than any vertebrate. Vertebrates are animals with backbones, like us, fish, birds, reptiles. So yeah, older than tortoises. Those ancient ocean quahog clams live longer, but they don't have backbones. For vertebrates, the shark is the king of long life.
Oh, how long are we talking?
Okay, get ready for this. Before 2016, people knew they lived a long time. Maybe 100 years, they guessed?
Which is already pretty old for a shark.
Right. But then a team of scientists, led by a marine biologist named Julius Nielsen, did some amazing detective work. They studied 28 different female Greenland sharks.
Okay, but how do you tell a shark's age? It's not like they have birth certificates. And you said they don't have bones, just cartilage, so you can't count rings like a tree or a bony fish.
Brilliant question. That was the big challenge. They couldn't use the usual methods, so they got clever. They looked at the shark's eyes.
The eyes, the cloudy eyes you mentioned.
Exactly. Specifically, the very center part of the eye lens is called the nucleus. Now, the cool thing is this core part of the lens forms before the shark is even born.
Okay.
And that tissue, that tiny core, never changes. It doesn't get replaced or repaired throughout the shark's entire life. It's like a little time capsule from its birth.
Wow. So it holds a chemical signature from when the shark was just starting out.
Precisely. So they used a technique called radiocarbon dating on that lens nucleus tissue.
Radiocarbon dating. Isn't that what they use for, like, ancient artifacts? Measuring carbon?
Sort of, yeah. It measures a specific type of carbon, carbon-14. Here's the clever part. Back in the 1950s and 60s, there was a lot of nuclear bomb testing.
Right, unfortunately.
That testing released a big pulse of extra carbon-14 into the atmosphere and eventually into the oceans. It created a very clear time marker in the environment.
Ah, so if the eye tissue formed before that pulse, it would have a different amount of carbon-14 than tissue formed after.
You got it. By measuring the carbon-14 levels in that oldest central part of the eye lens, they could figure out if the shark was born before or after the 1960s bomb pulse, and then calculate backwards how old it was based on how much the carbon had naturally decayed over time.
That is seriously cool science. So what did they find? How old was the oldest one they tested?
Okay, the results were staggering. They confirmed absolute minimum age for the oldest female was 272 years old.
272. That's already incredible. Born in the 1700s.
Already amazing, right. But wait, based on the size of that shark and their growth models, their calculations suggested she could have been much older. Their best estimate? Possibly as old as 512 years old.
512. No way. Seriously.
Seriously, 512 years. It's hard to even comprehend.
Let's try. A shark swimming around right now could have been born in the 1500s.
Potentially, yes. Or certainly the 1600s or 1700s. Think about it. A 500-year-old shark was alive when Shakespeare was writing plays.
Wow. It was swimming in the Arctic when the United States was founded.
It was already ancient when the Titanic sank. It's seen centuries of history pass by, just silently gliding through the deep. A true living time traveler.
Mind blown. Okay, what about its name? You said Somniosus microcephalus. Does that tell us anything?
It actually tells us quite a bit. It's Latin and Greek combined. Somniosus comes from the Latin word somnus, which means sleep.
Sleepy. Why sleepy?
Because of that record-breaking slowness we mentioned, it just looks like it's half asleep as it moves, drifting, slow, measured, so sleepy.
Okay, makes sense. And microcephalus. Sounds like micro for small.
Exactly. Micro means small, and cephalus comes from the Greek word for head. So its scientific name literally means the sleepy small head.
Ah, sleepy small head. I love it. And it fits, right? You said it has a small head for its huge body.
Yep, its head is quite short and rounded compared to its massive, almost cylindrical body. It's a good way to identify it.
Cool. So where does sleepy small head fit in the big animal family tree?
Good question. It belongs to a big group called the Chondrichthyes. That's the fancy science name for the cartilage fish club.
Cartilage fish club. I like that better. So that includes all sharks and rays too.
All sharks, skates, and rays, yep. And the key thing, the reason for the name, is their skeleton.
Right. You mentioned no bones, just cartilage, like the stuff in our nose and ears.
Exactly that stuff. If you wiggle the tip of your nose, that flexible but tough material, that's cartilage. The entire skeleton of a Greenland shark and all its club members is made of that.
Why is that an advantage? Does it make them lighter?
It does. Significantly lighter than if they had heavy bones. It also makes them more flexible. It's a really successful ancient design for moving efficiently in water.
And the Greenland shark is part of a smaller group within that club.
Yes, it's in the sleeper shark family, the Somniosidae. And as the family name suggests, they're all known for being pretty slow-moving, energy-saving specialists. The Greenland shark is just the extreme example.
Yeah.
Okay. Let's think about the shark's body itself. If you had to design a creature to survive for centuries in freezing, crushing depths, saving every tiny bit of energy, well, you'd probably end up with something like the Greenland shark.
It's not built for speed then. Not like a pointy, sleek great white. You described it as thick, like a torpedo.
Exactly. Think less fighter jet, more deep-sea submarine. It's thick-set, cylindrical, incredibly robust. Everything about it shapes as efficiency, not flashy speed.
And you mentioned something about its fins being a clue.
Yes, look at pictures of it. Compared to its enormous body, its fins, the dorsal fin on top, the pectoral fins on the sides, they're surprisingly tiny.
Huh. I see that now. Why are they so small?
Well, think about fast sharks, like a mako. They have big, powerful fins for generating speed, making sharp turns, bursting after prey.
Right, like wings and rudders on a plane.
Kind of, yeah. Tiny fins mean the Greenland shark isn't built for any of that. It's not chasing things down in a high-speed pursuit. It's built for steady, efficient, low-energy cruising, like a marathon runner who's mastered gliding just in super slow motion.
Okay, so the shape is efficient, the fins are small.
Yeah,
What about its skin? Shark skin is weird, isn't it? It's not smooth.
not smooth at all, and definitely not slimy like many fish. Greenland shark skin, like most shark skin, is covered in millions upon millions of tiny, hard, V-shaped structures. They're called dermal denticles.
Dermal denticles. Dermal means skin, and denticles sound like teeth. Skin teeth.
That's literally what it means, skin teeth. If you were ever able to gently stroke a shark, you'd feel it. One way it might feel smoothish, but the other way it feels rough, almost like sandpaper.
Okay, skin teeth. Sounds tough. What's the point? Armor?
That's definitely one major benefit, yes. They act like a flexible suit of armor. Think of it like natural chainmail. It protects the shark from scratches and scrapes, maybe bumping against rocks or ice on the dark seafloor. Really important in that harsh environment.
Makes sense. Armor plating? Is that all they do?
Nope. This is where the really cool physics comes in. The specific V shape and arrangement of these denticles do something amazing with the water flowing over the shark's body. They provide stealth.
Stealth. How can rough skin make it stealthy? Wouldn't it create more drag?
You'd think so, intuitively, but it's the opposite. When water flows over a smooth surface, it can tumble and create turbulence, which causes drag, slowing things down and making noise.
Okay.
But these V-shaped denticles are aligned in a way that channels the water. They force the water to flow in tiny, straight, parallel streams very close to the skin. This actually reduces the overall drag and turbulence significantly.
Whoa. So the rough skin actually helps it slip through the water more easily.
Way more easily. It means this massive 2,000-pound animal can glide with minimal effort, saving precious energy, and crucially for a slow hunter.
It makes it almost silent.
Exactly. No noisy turbulence giving it away. The dermal denticles act like a stealth cloak. It allows this giant to sneak up on prey or approach a potential meal with legendary quietness. It's incredible natural engineering.
A silent, armored, slow-motion submarine.
Got it. Okay, let's zoom in on the face again. You mentioned those cloudy eyes and something about parasites. That sounds a bit creepy.
It does look pretty creepy, yeah. Very often when scientists examine these sharks, they find these weird, dangly, whitish things attached right to the shark's eyeballs.
Ew. What are they?
They're actually a type of tiny crustacean, like a shrimp or crab relative called a copepod. This specific one, Omatocoida elongata, has specialized to live right on the Greenland shark's cornea.
The cornea. The clear front part of the eye. What does it do there?
It latches on and basically feeds on the eye tissue.
It eats the shark's eye. Well, it grazes on the surface layers, but as you can imagine, having a creature constantly attached to and munching on your eyeball causes problems, scarring, infections.
So, does it make the shark blind?
Very often, yes. Many, if not most, adult Greenland sharks are thought to be partially or even completely blind because of the damage caused by these parasites.
Blind. Okay, now I'm really confused. How can a giant predator survive, let alone hunt fast things like seals, if it can't see? That seems like a massive disadvantage.
It would be for almost any other animal, but here's where the Greenland shark turns a problem into, well, not really a problem at all. It's a masterclass in adaptation.
How so?
Remember where it lives. Thousands of feet down, under thick Arctic ice. How much sunlight reaches those places?
None. Pretty much zero.
Exactly. It lives in permanent, total darkness. So having eyes that are good at seeing light, well, they're pretty useless down there anyway. The blindness just doesn't matter that much.
Ah, okay, so the parasite is kind of like a freeloader, but it doesn't actually harm the shark's ability to get by because sight wasn't important to begin with.
Pretty much. The shark had already evolved to rely on other senses, way more powerful senses, to navigate and find food in the dark. Sight was secondary at best. So it has these amazing super senses, 4 of them, really.
Super senses. Okay, tell me about them. What's number 1?
First, super smell. All sharks have a good sense of smell, but the Greenland shark's is exceptional. It has these large nostrils called nares that are constantly pulling in water and analyzing it for chemical clues.
Like a swimming nose. You said it eats dead stuff, carrion, that sinks down.
Yes, that's a big part of its diet. And its sense of smell is perfectly tuned to detect the specific chemical signals given off by decaying flesh, even tiny amounts.
So it can smell a dead whale or seal from really far away.
Miles away, potentially. It just follows that scent trail through the darkness, like following breadcrumbs right to the source. Smell is probably its main tool for finding those big sunken meals.
Okay, super smell. What's next?
Second, super hearing, or maybe better called super vibration sensing. Sound travels incredibly well underwater, much better than in air, and this shark is tuned to low-frequency sounds.
Low frequency, like bass notes.
Exactly. Think deep thumps and rumbles, not high-pitched squeaks. It's listening for the sounds of struggle, a fish thrashing, maybe a seal moving awkwardly in the water column while resting. Those low-frequency vibrations travel far and signal potential prey. It hears the dinner bell long before it gets close.
Cool, super smell, super hearing. What's number 3?
Third, super touch, but it's touch at a distance. It uses its lateral line system.
Lateral line. I've heard of that. Fish have it too, right? What is it exactly?
It's amazing. It's basically a narrow canal filled with jelly and tiny sensory hair cells that runs along the side of a shark's body from head to tail. This system detects tiny, tiny changes in water pressure and movement.
No, it can feel things moving nearby without actually touching them.
Perfectly put. It's like distant touch. Imagine a fish swims by. It creates a little pressure wave in the water. The lateral line picks up that wave, tells a shark how big the object is, how far away, which direction it's moving. It lets the blind shark build a feel picture of its immediate surroundings in complete darkness.
That's incredible. Okay, smell, hearing, touch. You said 4 senses. What's the last one? The ultimate superpower.
Ah, yes. Fourth, the sixth sense electroreception. This is the truly unique shark superpower. If you look closely at a Greenland shark snout, you'll see hundreds of tiny little dark spots, like little pores.
Pores, what are they for?
These are the openings to the ampullae of Lorenzini. They're jelly-filled canals that act as incredibly sensitive detectors for electricity.
Electricity, like from power outlets. What generates electricity in the ocean?
Living things. Every time any animal moves a muscle, even just a fin twitch or the beating of its heart, it generates a tiny, faint electrical field.
No way. So the shark can sense the electricity from other animals' bodies.
Yep. It's like having a built-in fish detector. It doesn't need to see the fish, hear it, or even smell it sometimes. It can sense the faint electrical buzz of its nerves and muscles.
So could it find a fish hiding, like buried in the sand?
Absolutely. That's one of the classic examples. It can detect a flatfish, like a halibut, completely hidden under the sand, totally still, just by sensing the tiny electrical pulses from its hidden, beating heart.
That is a superpower. Okay, so even being blind, with super smell, super hearing, super touch, and super electricity sensing, this shark knows exactly what's going on around it.
Pretty much. It's perfectly equipped for life in the dark. Blindness is just not a big deal for this amazing hunter.
Let's go back to that speed thing again, because it still seems weird. You said its cruising speed is what, less than 1 mile per hour?
Around 0.76 miles per hour is the average measured speed. Yeah, incredibly slow. Even when it sprints, it barely gets above 1.5 miles per hour.
I mean, I can walk faster than that. I can probably crawl faster than its sprint speed.
Easily. An average person walks about 3 miles per hour. So, yeah, it's moving at maybe half the speed of a casual stroll.
Okay, here's the big question then, the diet paradox. If it's that slow, how on earth does it catch things like fast-swimming fish cod, salmon, and especially seals? Seals can swim really fast.
They sure can, up to 10 miles per hour, maybe faster in bursts. So the shark is definitely not winning any races. It can't chase them down.
So, how? Does it just wait for things to bump into it?
Not quite. The leading idea among scientists is the ambush hypothesis. It relies on stealth, not speed.
Ambush, like hides and jumps out. But where does it hide in the open water?
It uses the darkness and its silence. Think about seals. They need to breathe air, but they often hunt or rest deeper down. Sometimes they sleep in the water column drifting.
Okay, so they're just hanging out, maybe snoozing underwater for a bit.
Right. And the Greenland shark, using its silent approach thanks to those dermal denticles, and coming up from the pitch black depths below where the seal can't see it, it just glides slowly upwards.
Sneaking up from underneath while the seal is sleeping or distracted.
That's the theory. It gets incredibly close without the seal even knowing it's there. And then at the last moment, maybe a quick burst, and it strikes. It's a master of surprise, using patience and silence, not speed.
Wow, the ultimate stealth hunter. Okay, so it ambushes seals. What else is on the menu? You said it eats anything.
Pretty much. It's what scientists call an opportunistic generalist. That means it's not picky. In the Arctic, food can be scarce, especially deep down, so you can't afford to pass up a meal.
So whatever it finds, it eats.
Basically, yes. Lots of bottom fish, like halibut, skates, eels, various kinds of squid, even things like smaller whales if it gets the chance, maybe sick or young ones.
Okay, that makes sense. But then there are those crazy stories, finding land animals inside them, polar bears, reindeer. How does that happen?
Ah, yes, the legendary stomach contents. It's true. Scientists examining their stomachs have found remains, sometimes remarkably whole remains, of polar bears, moose, horses, and famously an entire reindeer, antlers included.
An entire reindeer.
Yeah.
How did it jump out onto the ice floe?
No, definitely not. We need to bust that myth right now. Greenland sharks do not hunt on land or ice.
Okay, good. So what's the real story?
The real story highlights another crucial role this shark plays. It's the Arctic Ocean's master scavenger, the ultimate janitor.
Janitor, cleaning up messes.
Exactly. Think about it. What happens if a reindeer tries to cross thinning ice and falls through? Or a polar bear dies on an ice floe, maybe of old age, and eventually slips into the water? Or a moose drowns trying to swim between islands?
They sink.
They sink down to the bottom, or they drift in the currents. And what has super smell tuned for finding large sunken carcasses?
The Greenland shark. It's following the scent trail to these drowned land animals.
Precisely. It finds this massive, unexpected feast carrion on the seafloor and cleans it up. It's recycling nutrients that would otherwise be lost from the land into the deep ocean ecosystem. It's incredibly important.
Wow. Okay, so it's not a land hunter. It's a deep sea recycler of land animals. That's even cooler.
Yeah.
But how does it eat something as big as a moose or a whole reindeer? Its mouth isn't that big, is it?
Good point. It can't swallow them whole. It needs a way to take manageable bites out of enormous food sources. And it has the perfect toolkit for that. Its specialized teeth and bite.
Specialized teeth. How are they different?
They're completely different on the top and bottom jaws. The upper teeth are narrow, pointy, almost like little hooks. They're not really for cutting.
What are they for then? Stabbing.
Gripping. Anchoring. Imagine the shark comes across a huge dead whale. It bites down and those sharp upper teeth sink in and hold the shark firmly attached to the carcass, like grappling hooks.
Okay, so it anchors itself with the top teeth. Then what?
Then the lower jaw goes to work. The lower teeth are totally different. They're wide, square-ish, and have serrated edges like tiny saws. And they're interlocked tightly together to form a continuous cutting blade.
A saw blade on the bottom jaw.
Exactly. So once it's anchored with the top teeth, the shark swings its head and body in a rolling, twisting motion. That motion drags the sharp, saw-like lower jaw through the flesh.
Carving out a chunk.
And because of the way it bites and rolls, it carves out a big, round plug of meat. Scientists literally call it the cookie cutter bite. It allows this relatively slow shark to efficiently remove huge amounts of tissue from prey much larger than itself, perfectly designed for scavenging giants.
The sleepy small-head cookie-cutter janitor. What a title.
Okay, we need to tackle maybe the biggest survival puzzle of all. How does the shark physically handle living in water that's hovering right around freezing, sometimes even below the freezing point of fresh water, down to maybe -2 degrees Celsius or 28 Fahrenheit?
Right. Wouldn't its blood freeze? Wouldn't ice crystals form inside its body? That sounds instantly fatal.
It would be for almost any other vertebrate. But the Greenland shark has a built-in biological antifreeze.
Antifreeze, like the stuff you put in cars.
Very similar idea. It keeps high concentrations of certain chemicals dissolved in its blood and all the tissues throughout its body. It's a specific chemical cocktail.
What chemicals? Anything special?
Two main players. High levels of urea, which is a waste product for us but useful for the shark, and another compound called TMAO. That stands for trimethylamine N oxide.
Urea and TMAO.
Mm-hmm.
Okay, how do they work as antifreeze?
By having so much of this stuff dissolved in their body fluids, it effectively lowers the freezing point of that fluid. Just like adding salt to water makes it freeze at a lower temperature, adding urea and TMAO means the shark's internal fluids won't turn to ice even when the water around it is at or below freezing. It prevents those deadly ice crystals from forming in its cells.
That's brilliant. Built-in winter protections. Does that TMAO stuff do anything else? You mentioned the crushing pressure, too.
Ah, yes. TMAO is a bit of a wonder chemical for deep sea life. It performs a second crucial job. It helps protect the shark's body against that immense pressure.
How does it do that? Pressure proofing.
Kind of. Extreme pressure, thousands of feet down, tries to squash and distort the delicate, complex shapes of proteins, the building blocks of cells and tissues. If proteins get squished out of shape, they stop working, which is lethal.
Okay.
TMAO molecules actually help stabilize proteins. They sort of push back against the water pressure on a molecular level, preventing the proteins from getting deformed. It acts like a protein protector or a molecular shield.
Wow. So the same chemical cocktail that stops it from freezing also stops it from being crushed by pressure. One solution for two giant problems.
It's an incredibly efficient adaptation, but like many things in evolution, this brilliant solution comes with a significant trade-off, a major side effect.
A side effect. What could be bad about having antifreeze and pressure protection?
The side effect is that having such high concentrations of urea and TMAO saturated throughout its body makes the shark's flesh highly poisonous if eaten fresh.
Poisonous. Seriously.
Mm-hmm.
The shark itself is toxic.
The fresh raw meat is, yes. To mammals, including humans and sled dogs. Those same chemicals, especially the TMAO interacting with other compounds, act as a potent neurotoxin.
Neurotoxin affects the nerves. What happens if something eats it?
It can cause symptoms that sound like extreme drunkenness, loss of coordination, staggering, vomiting. But it can also lead to muscle tremors, convulsions, seizures, difficulty breathing, and in severe cases, even death.
Whoa. Okay, that explains a lot. I remember reading Inuit stories or legends about sled dogs going crazy or dying after eating Greenland shark. So it was the toxins.
Exactly. And it also explains why the fresh meat has such a strong, unpleasant smell, often described as being like ammonia or strong urine. Urea is the main component of urine, after all. The smell is a warning sign.
So this massive potential food source roaming the Arctic was basically off limits because it was poisonous.
For a long time, yes. But human ingenuity found a way. This leads us to the amazing and kind of strange story of Hakarl from Iceland.
Hakarl. I've heard of that. Fermented shark, right? Supposedly smells terrible.
That's the one. The people of Iceland figured out over centuries how to make the poisonous Greenland shark meat safe to eat through a long, careful process of fermentation and drying.
How do they do it? How do you get the poison out?
It's a pretty intense process. Traditionally, they dig a shallow pit, place the shark meat inside, and cover it with sand, gravel, and heavy stones on top. Or nowadays, they might use large plastic containers with drains.
Why the heavy stones? To squeeze it.
Exactly. The pressure squeezes out the toxic fluids containing the urea and TMAO. This pressing and initial fermentation stage lasts for 6 to 12 weeks, depending on the season.
Weeks underground or squashed in a box?
Yeah.
Okay. Is it safe then?
Not yet. After the pressing, the really toxic stuff is mostly gone, but it needs further processing. They cut the meat into large strips and hang it up to dry in special open-air sheds.
Hanging shark meat. For how long?
For another 4 to 5 months. The wind and air continue the drying and curing process, allowing beneficial bacteria to further break down any remaining toxins and develop the unique flavor.
Unique is one word for it. So after all that burying, pressing, hanging for months, it's finally safe.
Yes. By the time hot roll is ready, the toxins are neutralized. But as you heard, it retains that incredibly strong smell of ammonia and a very acquired taste. It's considered a national dish in Iceland, but definitely one of the world's most challenging foods. A perfect reflection of the shark's own toxic survival strategy.
Wow, what people will do to make food safe. From poisonous survivor to smelly delicacy. Amazing.
Let's connect back to that super slow motion lifestyle. We know the shark moves slowly, lives incredibly long. This slow pace affects everything, especially how it grows and when it starts a family.
Right, the slow metabolism is key. You said it grows really slowly. Like how slowly?
Glacially slowly. Estimates are around just 1 centimeter per year, maybe even less for the really big old ones.
1 centimeter, that's less than half an inch. A year.
Yep, think about that. To grow just 1 foot, it would take about 30 years. It takes this shark maybe 5 years just to grow the length of a pencil.
Patience on a whole different level. So if it grows that slowly, what does that mean for Well, for growing up, becoming an adult.
It means it takes an extraordinarily long time. This is probably the single most astonishing fact about its life cycle. Based on their growth rate and the size at which they seem to become able to reproduce, scientists estimate that a Greenland shark has to wait. You ready for this? About 150 years just to reach sexual maturity.
150. Yeah, years just to become a grown-up shark capable of having babies.
150 years, minimum. Maybe even longer for some. That's why we joke about it being the 150-year-old teenager.
That's unbelievable. So a shark born today,
Yeah.
let's say in 2024, it won't be ready to have its own pups until the year 2174 or later.
That's the math. You and I, well, we'll be long gone before a shark born today is considered an adult in its own world. It completely changes how we have to think about protecting them.
No kidding. So, okay, it takes forever to grow up. When they finally do reproduce, how does it work? Do they lay eggs like some sharks?
They don't lay eggs externally, no. They use a method called ovoviviparity. It's kind of an in-between strategy.
Ovoviviparity. Okay, break that down for me.
Ovo means egg. Vivi means live birth. So the mother develops the eggs, but she keeps them inside her body instead of laying them somewhere.
So the eggs hatch inside the mom.
Exactly.
Like-
The pups hatch from their egg sacs while still inside the mother. They live off a big yolk sac that was part of the egg, continuing to grow within her. It's like she's a living, swimming hatchery.
And then she gives birth to little live sharks.
Yep. She eventually gives birth to live, fully formed pups. And they're not tiny. They're already about 15 inches long, maybe a bit bigger. Big enough and strong enough to survive on their own in the harsh, deep, cold environment right away.
Okay, so live birth after hatching inside. Got it. But if they live so long and reproduce so late, how much do scientists actually know about this part of their lives? It must be hard to study.
Incredibly hard. This is where we enter the realm of the great unsolved mysteries. Because their lifespan is measured in centuries and they live so deep and remote, there are huge gaps in our understanding of their family life.
Like what? What don't we know?
Mystery number 1, the mating game. Simple question. How do they find each other and mate? No human has ever seen it happen. Think about it, these 150-year-old plus giants roaming possibly vast areas of the deep, dark ocean. How do they meet up? What triggers it? We just don't know.
Do they have courtship rituals? Do they communicate somehow?
We have no idea. The only clue is that sometimes female sharks are found with bite marks or scars that look like mating scars seen on other shark species where the male bites to hold on, but that's just a guess. Where, when, how? Total mystery.
Okay, mystery number 1. Finding a date when you're 150. What's mystery 2?
Mystery number 2, the lost nursery. Where do the pregnant females go to actually give birth? It's assumed they must migrate to specific areas, pupping grounds or nurseries that are safe and suitable for the newborn pups.
Somewhere protected. Maybe specific depth or temperature.
Probably. But no one has ever found one of these Greenland shark nurseries. Where are these secret spots where hundreds of baby Greenland sharks are born? It remains one of the Arctic's biggest secrets.
Wow. And you mentioned another mystery related to pregnancy.
Mystery number 3, the longest pregnancy. Given how slow everything else is in their life cycle growth, maturity scientists strongly suspect their gestation period, the actual time they're pregnant, must also be incredibly long.
How long are we talking? Longer than an elephant's 2 years?
Way longer. The estimates, and they are just estimates based on modeling, range from 8 years up to possibly 18 years for a single pregnancy.
18 years. Pregnant for almost 2 decades.
If true, it would absolutely shatter the record for the longest pregnancy of any animal on Earth by a huge margin. But again, we haven't been able to confirm it directly. It's inferred from their slow biology.
Okay, these are huge mysteries. Mating, nurseries, pregnancy length. Was there anything else we used to get wrong about their reproduction?
Yes, a big one. For decades, the only real data point we had on litter size came from one single pregnant female caught a long time ago. She had only 10 pups inside her.
Only 10. After waiting 150 years and maybe being pregnant for a decade, that sounds really inefficient. Like, how could the species survive with such low numbers?
Exactly. Scientists were puzzled by that too. The math just didn't seem to work for long-term survival if they waited that long for so few offspring. It didn't fit.
So was that one shark just unusual? Or was the science wrong?
It seems that first shark might have been unusual, or maybe something had happened to her other pups, because more recently, Dr. Nielsen, the same scientist who figured out their age, made another huge discovery.
What did he find?
While examining the reproductive system of another adult female, they didn't find hatched pups, but they found unfertilized eggs. And the number was astounding. She had 649 large, viable-looking eggs inside her.
649. Wow. From 10 to over 600, that changes everything.
Completely changes the picture. It led to a whole new hypothesis about their strategy. It suggests they might use a reproductive lottery approach.
Lottery. Like buying lots of tickets.
Kind of. They wait an incredibly long time, 150 plus years. But when they finally do reproduce, they go big. They produce hundreds of eggs to maximize the chances that at least some will survive. The new thinking is that a single litter might actually contain somewhere between 200 and 300 live pups.
Ah, that makes much more sense. Invest rarely, but invest hugely when you do. It's a strategy built for centuries, not years.
Exactly. A few hundred pups at a time gives the species a much better chance of persisting across those vast timescales, even if individuals reproduce only a few times in their incredibly long lives.
So we've established this shark is ancient, slow, mysterious, and incredibly well adapted. But what's its actual role out there in the Arctic Ocean? What's its job in the ecosystem?
It actually plays two really crucial roles, ecologically speaking, two main jobs.
Okay, what's job number one?
Job number one, apex predator. Even though it's slow in its deep, cold world, it sits right at the top of the food chain. There isn't much down there that preys on an adult Greenland shark.
So it helps control other populations, like the seals and big fish it eats.
Yes. By preying on seals and large fish like halibut, cod, and skates, it helps regulate their numbers, keeps those populations healthy, and influences the whole structure of the food web below it. Classic apex predator role.
Okay, top predator. What's job number two? You mentioned already.
Job number two, deep sea janitor. This scavenging role is hugely important. By consuming those massive carcasses that sink from above, whales, seals, polar bears, reindeer, whatever falls in it, prevents all that energy and those nutrients from just getting buried and lost on the seafloor.
It recycles them back into the system.
Exactly. It acts like a nutrient elevator, bringing energy from the surface or land back into circulation in the deep sea food web. It's essential for keeping that nutrient-poor environment going, a vital cleanup crew.
Apex predator and master janitor.
Okay.
Got it. But you also mentioned something else. Something about it being like a time capsule, because it lives so long.
Yes, this is a sadder, more recent job. It's acquired unintentionally. Because it lives for centuries and sits at the top of the food chain, it's become a living time capsule of ocean pollution.
How does that work? Does it just soak up pollution from the water?
It happens through a process called biomagnification. Think of it like a pyramid. Pollutants, like mercury or certain industrial chemicals, get into the water at low levels.
Okay.
Tiny plankton absorb a little bit. Then a small fish eats thousands of plankton, concentrating the pollutant in its body. Then a bigger fish eats hundreds of those small fish, concentrating it even more.
And the Greenland shark eats those bigger fish, or seals that ate those fish. So it gets the concentrated dose from everything below it.
Precisely. And because it lives for potentially 500 years, it's accumulating these pollutants in its tissues, its muscles, its liver over its entire incredibly long life. The concentration magnifies hugely at the top.
So its body literally contains a record of the pollution levels over the past few centuries.
That's exactly right. Scientists can analyze tissue samples from Greenland sharks and get a snapshot of how ocean contamination has changed over hundreds of years. It's a valuable, if worrying, archive of environmental history stored in living flesh.
A living pollution archive.
Yeah.
Wow. Okay, so despite being this ultimate survivor for centuries, is it doing okay now in our modern world?
Unfortunately, no. Despite its incredible resilience, the Greenland shark is now listed globally as vulnerable to extinction, and it's facing some serious threats it never encountered before.
Vulnerable. That's serious. Why? What's the biggest problem for such a tough creature? It seems like it should be invincible.
Its greatest strength, its longevity, has become its greatest weakness. It's caught in what scientists call the longevity trap.
The longevity trap. What does that mean?
It means that because it takes so incredibly long to mature 150 years, remember, the population is extremely slow to recover if adult sharks are removed.
So if you lose an adult shark, you're not just losing one animal.
You're losing an animal that might have reproduced for potentially hundreds more years. If a fishing boat accidentally catches, say, a 100-year-old Greenland shark, that shark hasn't even had a chance to reproduce once. You've wiped out potentially hundreds, maybe thousands of future pups that shark might have produced over the rest of its super long life.
Wow. So the population just can't bounce back quickly from losses?
Yeah.
One accidental death has huge ripple effects across centuries.
Exactly. The species is fundamentally ill-equipped to handle high rates of adult mortality. So what's causing those losses?
Fishing.
Yes. The number one threat, by far, is bycatch.
Bycatch. That means caught by accident, right? When fishers are trying to catch something else.
Precisely. Huge industrial fishing fleets operate in the North Atlantic and Arctic, targeting fish like Greenland halibut, cod, redfish. They use massive nets called trawls that drag along the bottom or deploy long lines with thousands of baited hooks.
And the slow-moving Greenland sharks just get scooped up in the nets or attracted to the bait.
Both. They're too slow to escape the giant trawl nets. And their amazing sense of smell leads them right to the easy meals offered by the thousands of baited hooks on long lines. They get caught unintentionally in huge numbers.
And many of them were probably those teenagers, right?
Mm.
Under 150 years old,
Huh.
caught before they could ever reproduce.
That's the tragic reality. A huge proportion of the bycatch is likely sharks that haven't reached maturity yet, hitting the population right where it hurts most.
Is that the only major threat? Or is there more?
There's another big one looming, connected to the first. Climate change.
How does climate change affect a deep, cold water shark? Is it the warming water itself?
The warming water might force them to shift their range, maybe go even deeper to find their preferred cold temperatures. But the more immediate and perhaps bigger impact of climate change in the Arctic is the melting sea ice.
Melting us. How does that hurt the sharks? Does it take away their habitat?
Indirectly. Historically, vast areas of the Arctic Ocean were covered by ice for most or all of the year, making them inaccessible to large fishing vessels. That ice acted like a natural protector for the sharks' home turf,
But now the ice is shrinking.
opening up huge areas of previously protected Arctic waters to increased fishing pressure. More boats can get into these areas for longer periods, setting more nets and lines. So climate change is basically opening the door for the primary threat bycatch to become even worse.
Oh, wow. So melting ice means more fishing boats, which means more accidental catching of these super slow-to-recover sharks. It's a double whammy.
It's a really concerning combination of threats for an animal that operates on such a slow, ancient timescale.
What an incredible exploration we've had today. We journeyed into the freezing depths to meet the Greenland shark.
The 500-year-old ghost of the Arctic.
We learned it's the longest living vertebrate, using natural antifreeze to survive the cold, and navigating total darkness with like 4 different superpowers.
Super smell, super hearing, super touch through the lateral line, and that amazing sixth sense electroreception. Plus, the cookie cutter bite.
And that mind-bending fact that it might take 150 years just to become a teenager in shark years.
It's a creature perfectly adapted for patience, for slow, steady survival across centuries.
But we also heard that its incredible slowness makes it vulnerable now. Caught accidentally in fishing gear, facing a changing Arctic.
Its ancient survival strategy is struggling to cope with our fast-paced modern world.
And here's something amazing to think about. We only really figured out how old these sharks are in 2016. That's super recent.
It really is. The story of the Greenland shark is, in many ways, just beginning for us humans. There are still so many huge mysteries left to solve.
Those big ones you mentioned, where do they actually mate? Where are those secret underwater nurseries? How long is that pregnancy?
We just don't know. Finding those answers will require new technology, new ideas, and the next generation of ocean explorers.
That means you, listening right now. Maybe you'll be the one to help invent a tiny camera that can follow a Greenland shark for years, or figure out how to find those hidden pupping grounds. The ocean still holds so many secrets.
The Greenland shark survived for hundreds, maybe thousands of years by being slow, patient, and perfectly in tune with its environment.
But now, it needs our help. Protecting this ancient animal, this living piece of history, means being smarter and more careful about how we treat our oceans, especially the Arctic. It means reducing bycatch, understanding its needs, and giving it the space and time it requires.
It survived through patience. Maybe we need a little patience and care to make sure it survives the future, too.
We really hope you enjoyed diving into the world of this truly remarkable creature with us today. It shows just how much wonder is still hidden in the deep.
Absolutely. Thanks for joining us, everyone.
Thank you so much for listening, explorers. We'll see you next time for another adventure on Saltwater Stories.